Всех уволил. Да, уже.
Что-то хотел, я ездил на конференцию. И там, значит, было 2 или 3 человека из Китая. Ну, то есть буквально вот, все участники, 2-3 человека, не понимали русский язык. Вот, но, в принципе, организаторы все заставляли на английском выступать.
Ну, вот это правильно.
Конечно. Ну, и тем более такая, ну, люди говорят, ну, там, что, 2 человека.
Не, ну,
Ну,
конечно, если мало того, все это же расползается, потому что если докладчиков не приучить, они, значит, на других конференциях тоже будут требовать. А когда все закончится, и нам собственно, снова будет много иностранных участников, но никто не поедет.
So, ladies and gentlemen, today we have an unusual seminar because it's not at 11 but at 2 p.m. For some internal reasons. And we have a great pleasure of listening today to our own speaker, Kirill Bazarov, who recently got his PhD from FISTEC, as far as I understand. And even now you started some new job, right? Or you are about to start, but you are still with us in some sense.
Yeah.
Okay, so please.
Okay. Okay, so first of all, I would like to thank the opportunity to give a talk here. It's an honor to give a talk. And today I'm going to talk about chiral asymmetry in the Photoeffect with Vortex Photoelectrons. The talk is based on our papers with my co-author Толстихин Oleg Isakovich. And okay, let's move. I'll start with extremely simple things because I would like to start with some basic principle of photoionization. And of course, everybody who knows something about photoionization knows this material. Yes, but this fact that it's so simple makes it's important. Let's consider the molecule and electrons in this molecule. We work in single active electron approximation. It means that we have some potential and some effective potential and one electron. At past infinity, this electron is in initial state here. And when this electron interacts with external, for example, photon or any field, its state starts to change. And as we know, we have some initial state when evolution operator from past infinity to future infinity, and we get final state of this electron. Roughly speaking, this final state, it's how to say, it's a complex structure with flux to infinity. And when we talk about photoelectrons, we think about how to say particles, point-like particles at infinity, but in fact, it isn't true. The true is that we have some complex final state, and when we detect particles at special infinity by some detector, and what is the procedure of detection? It's some projection, this complex final state, to some internal state in the detector. So in fact, this new some state, it's a property of the detector. This state is associated with the detector. So the the probability is squared projection. Okay. Note that we don't have electrons like particles at infinity. We have some detector, some state associated with this detector, and this final state. And of course, in quantum mechanics, we know that there is a golden rule, and within dipole approximation, we have the following formula of the differential cross section. It represents the number of electrons in a state nu per unit time and per unit flux of the photons. And here, dipole matrix element is given by the following formula, where here we have some photon polarization vector, and note that this psi nu is a final state. And note that we don't concretize which state we use, it's just some final state of the electron. And in general, we can consider whatever we want. We can consider any state psi nu. Okay, so it's just we limit just our fantasy. In literature and in the majority of the experiments, final states is considered to be a plane wave states. So we have electron at infinity. In special infinity, it doesn't feel the target, the molecular, for example. And at infinity, wave function of this electron solves free Schrödinger equation. And we can consider any in general. It's a simple things, but I repeat it a few times because this is one of the key points of our work. In general, we can consider any set of solutions of the following equation, right?
You assume that the mass and the Planck constant are equal to 1.
Right. The mass of the electron and Planck constant
And charge.
and charge. Right.
Both the two units.
Is the answer correct? Since you are working in the atom or the orbital moment, or the molecular orbital, so it shall be the lumma of the molecular orbital or the S or P or D.
It's an equation for the electron at special infinity. So we have molecular here, its potential here, but at special infinity, far away from the molecular, electron doesn't feel the molecular, and of course it's like a scattering state, where there is the wave function have the main part and suppressed. Okay, do you understand me? Sorry. Right. Fine. So basically, when we speak about solutions of this equation, it's used to consider.
Sorry, how do you need to normalize per unit flux, whatever, or why do you have just unnormalized exponent?
Okay, so here these functions psi nu normalized by orthogonality and completeness relations of these functions. So in fact here with these functions should be normalized like factor 1 over square root of 2 pi power 3 or something like that. And these Bessel functions have their own normalization, but now let's ignore normalization factors. So the set of solutions of this Schrödinger equation normally considered by plane waves. It's states with fixed momentum. So at infinity, electrons have fixed momentum k. And quantum numbers here, because we have fixed total energy, is just an angle of vector k. So we have two quantum number theta and phi. But we can consider another set of solutions of this Schrödinger equation For example, we can fix the projection of angular momentum on some axis, for example, z, and then the complete set of solutions of this equation is called vortex states and given by the following formula. We have along z direction there is moving with constant momentum, but in the
I'm sorry, to interrupt, but I think that that expansion of plane wave, it is if you through JM, is when you live in the plane. In 3D, it's normal scattering, 3D scattering theory, and it's kind of spherical wave. Why is it because your electromagnetic field is coming in a particular direction? Why do you have axial symmetry instead of spherical one? Can your electron be emitted in all three directions? Why? Because with this is for cylindrical symmetry of the problem, isn't it?
Okay, that's why I started with. Okay, a good question. So we have nu here is the final state of an electron. The energy of this final state is fixed by energy conservation rule, right? But still, for a fixed energy, we have infinitely many solutions of this equation. So in general, we can consider any solution of this equation, right? Usually, we want to so we can find a set of solutions of this equation in any basis. For example, Descartes basis or Cartesian basis here it's a plane wave. Spherical coordinates it's a spherical waves, but also cylindrical. In the cylindrical coordinate system we have the following solution. Okay, all these solutions can be connected with each other by unitary transformation. So it's just a complete basis in space of solutions of Schrödinger equation. So there is no, how to say, preferred one. These Bessel functions, how to say, why we prefer plane wave than Bessel functions?
Yeah,
Okay.
the final state, nu, denoted by nu, of course, is not what Kirill is showing. He is showing solution of the free Schrödinger equation, which defines the asymptotics of this new state. Nu is a scattering state with the asymptotics given here. For example, the plane wave must be a term must be added scattering amplitude times outgoing spherical wave. So the usual scattering state used in scattering theory. So he shows only the asymptotic part of this state, which determines the set of quantum numbers of the photoelectron. In one case, it's plane wave, which has definite momentum in the asymptotic region. In the other case, it's vertex, which has these three quantum numbers denoted by nu in the asymptotic region. And there are actually many other sets possible, because this Kirill equation, which is a free Schrödinger equation for free electron, can be separated in 11 systems of coordinates, and each system of coordinate provides a possible asymptotic boundary condition for the appropriate scattering state. Scattering.
Yeah, I agree. I understand. Tell me just your choice of z axis. I know that I can use coordinate system.
This is this axis with respect to which n quantum number is defined. It's our choice. We choose.
Yeah, what I'm asking, what is it? Is it from the molecule to the detector, or what? What is it? Your particular choice?
Detector. That's right.
Yeah, that's fine, because there is a selected direction.
Yes,
I'm happy. I just wanted to find out where that goes. Thank you.
The detector defines the axis with the vertex axis.
Okay, nice. Thank you. So, okay, let's continue. And why we consider vortex electrons? Basically, again, we can consider whatever we want here. We can consider any state nu, but it's like a fantasy. But vortex electrons, we fixed angular momentum, is produced recently in experiment in 2010 by this forked grating. Let me say a brief review of this idea. On the right hand side, we have schematic. It's a sketch of how this real grating work. If we start with incident plane waves, when this fork splits the beam into a few beams, with change momentum. For example, if we start from momentum 0, when there is a beam with 0 momentum still, negative momentum and positive momentum. So this particular grating splits incident beam into 3 beams with -1 momentum, 0 and +1. You can see here where is a ring-shaped profile of the Bessel function with the first with index 1. Okay, and the profile of this grating is constructed by holography ideas. We have some vortex here plus plane waves. It's a like wave. Actually, this profile splits beam in different directions. We can combine it. We have interference picture and binarize this colored picture to this grating. Okay, so 15 years ago, vortex electrons was produced and observed the first time, and since this observation, there is a huge growth of interest to the vortex electrons. Sorry?
But what's the size scale? It's 1 micrometer is the characteristic size of
grating. Because
that means that the wave vector and wavelengths of electrons must be of the same order.
It's a perpendicular, how to say. We have two momentums perpendicular to the gratings and along to the grating and along the grating. So this momentum can be whatever we want, but momentum in the plane, actually, this grating gives to electron perpendicular momentum like 1/1 micrometer. It's because how we produce this grating, we have some foil, and by some laser we have to cut stripes. Okay, so our main statement from our work, we considered photo effect, where the final state of the electron is a vortex state. So instead of the well-known differential cross-section in the plane wave case, we have partial vortex differential cross-section, which represents how much electrons how much electrons comes from ionized molecule to the state with fixed projection of the angular momentum, and fixed theta q is a parameter. I showed it was shown before, but actually let's move. I'll recall what it means later. Also, we have particular vortex cross-section because we have some parameter theta q here. M is angular momentum. We have fixed energy because energy conservation. If we fix a momentum, integrate over the third quantum number, we have this partial vortex cross-section. It represents how many electrons will be in state with angular momentum m. And total cross-section, if we sum of the final momentums, we have a total cross-section. And note also that this total cross-section is independent of the choice of final states. So the total cross section in the plane wave case is similar with total cross section in the vortex state. Okay, let's continue. And so we are interested in these observables. And in our works, we calculate these observables within zero range potential model. Let me say a few words about this model. We can consider any target, but we consider complex target. It's for example, molecular. Namely, we consider glyceraldehyde molecular. It's a chiral complex molecular, and we describe it by the zero range potential model. So recall we work in single active electron. So our electron live in the following potential. Yeah, it's a sum over these zero range potentials. These potentials is zero everywhere outside the atoms. So n is the number of atoms. This is the positions of concrete atom, and kappa is the depth of well on each atom. Okay, so we calculate our pictures within this model. I would like to continue and doesn't discuss the model. And also there are two types of problems. First is we have single molecule, and it's frozen. Okay, so it's like, how to say, we can consider, one can consider just one single molecule and consider a photo effect on it. But in fact, in the real experiments, where ensemble of randomly oriented molecules, so actually from the experimental point of view, it is more useful to consider observables averaged over molecular orientations. So we have some, for example, if we have some observable O for the one molecule, when this bracket represents averaging over molecular orientation, as we know, the orientation of the some object is defined by three Euler angles. So we just integrate over these three Euler angles, which represents the concrete orientation of the molecule. Okay, let's move to the pictures. Here, not averaged. It's for one fixed molecule. The blue line represents circular polarized field. P is the polarization of the photon. If it's polarized if the photon is circular polarized, we have blue total cross section, and if the photon is linear polarized, we have black total cross section. And you can see here the red line represents the total cross section averaged over molecular orientations. So within our model, total cross section starts at zero, of course. When grows, we have some peak at some photon energy, and when it decays to zero, as it should be, and how to say, the averaged quantity, the red, is somewhere between different polarization. But it's a total cross-section, but we can consider vortex cross-section. It's a cross-section which represents the probability to find an electron with the state with fixed angular momentum m. And of course, the dominant channel is m0. Okay, so the majority of the electron will be at the state with vorticity equals zero, but where a lot of electrons with these blue and red lines, a lot of electrons which will be at vortex state at infinity.
Wait a second. Polarization using the spin degree of freedom of the light of the orbital
Spin, no.
Spin.
secondly polarized photon. Or linearly polarized.
But the figures in that nature paper, so that creates the angular momentum.
No, the nature paper is about vertex electrons, not about vertex photons. There are also vertex photons, but it's different. We don't consider orbital angular momentum on the photon. Photon, in our case, has only spin if it is secondly polarized, non-zero spin, but it doesn't have internal so-called structure like, no.
Okay, that's
And also consider the following characteristic. P is a fraction of vortex photoelectrons at small energies. P0, which represents the fraction of photoelectrons without vorticity, is 1. It means that at low energy, all photoelectrons don't have vorticity. But when energy grows, where non-zero and like 1/2 contribution from vorticity from photoelectrons with vorticity, it means that actually vortex photoelectrons produce by such photo effect massively. And it's interesting to consider the overaged. You can see that this effect survive averaging over molecular orientation. And the most interesting part here that, for example, here we have averaging or averaged over molecular orientation partial cross section for polarized photon and photoelectron with vorticity. The blue line represents vorticity 1, the blue dashed line represents vorticity -1. It means that we consider photoelectrons with positive angular momentum and with negative angular momentum, and where is a difference between them, and this difference signs of chiral asymmetry in the observables, and our papers actually is devoted by such kind of asymmetries, and now we will discuss these asymmetries. So actually, these vortex electrons are chiral objects. It means that if you have some mirror here, for example, and we have some vortex states here, when on the other hand, as a mirror, we have vortex states with negative momentum m. Okay, so here we have plus m, here we have minus m. It means that these two objects are chiral and connected by inversal in the plane, mirror plane. Okay, and because vortex electrons these chiral objects, when vortex photoelectrons can be used as a chiral probe. And for example, one can ask, can we distinguish two mirror copies of the molecule, which calls enantiomers, by these vortex photoelectrons? And our answer is yes, and I'll show you how. So the main formula from our work is the following. It gives, so here we have some ensemble of the molecules, here just one, but we consider it ensemble. Here is the axis of, this is some fixed axis, and we can choose the direction of vortex photoelectron moving by this green line. Here is the angle theta. Photon, for example, circularized photon moves along this dashed line. And when averaged over molecular orientation differential cross section gives can be expressed by this formula. Here we have total cross section. It's not actually interesting for us, but here we have some simple, very simple structure of the dependence on the angle theta, capital theta, and we have only three terms here, L0, 1, and 2, and it means actually that for the after averaging over molecular orientation, we have a few observables. Of course, the total cross-section, which again is not interesting for us, and three constants B, L, P, M. P is a photon polarization. It can be plus or minus 1 is a circle polarization right and left, and P0 is a linear polarization, and photoelectron vorticity M. Okay, and sorry. And again, we have Q perpendicular and QZ, and they can be representarized by angle theta Q. So this theta Q is angles parameterized Q perpendicular and QZ. Okay, so we have the main observables by this blue box and a few parameters in it, P, M, L, and theta Q. And we have three chiral objects, molecular, molecular, which can be either in the, how to say, left and right version, because chiral molecules have two enantiomers. We have photon, which also can be chiral if it circularly polarized. And we have photoelectron, which again is a chiral object. And it is known that to probe chirality of something, we need to use some chiral probe. And the idea is that each of these objects can be used as a chiral probe for the others.
But intuitively, if you are using the dipole approximation, it feels like the photon polarization should not play any role.
No, it's play because let me get back.
I also have a question. Like, what is the energy of photon? Maybe this is quite important. I don't know, wavelength of how it's compared to the size of the molecule.
Okay, so first of all, about polarization vector. Of course, how to say, it depends. In the linear polarization case, this vector have only one component, but in the circular polarization, it has two components shifted by phase.
Okay, but if you're averaging over all possible orientations, then and moreover averaging over time, then
No time. Time, there is no time.
No,
It's
time is hidden here, but yeah.
okay. All right, maybe it's just wrong intuition. I just want to check.
Okay, it's because we average observable rather than amplitudes. It means that we squared the amplitude and then averaged squared amplitude. So that's why. If we average amplitudes, then will be no difference. Okay. About energy of the photon. We work in our work. We change the energy of the photoelectron. So of course, in our parameter was the energy of the photoelectron. So energy of the photon, of course, can be found by this energy conservation. So we have the energy of the photon is just the energy of the photoelectron minus ionization potential, which somewhere around 1 atomic unit. So we work about. Okay, so the energy of the photon, like a few atomic units. It's in electron volts. I don't know, maybe how much.
several tens of electron volts.
Right? It's this energy.
Sorry, energy of the
What? Rydberg energy, right?
Yeah, about that. Rydberg is half of atomic units, so several atomic units.
Yes, and I think dipole approximation in this case it doesn't work. Yes.
It works very well because 1 atomic unit, say, it's about 100 nanometer. 100 nanometer is much more than size of a molecule.
Okay.
Okay, so we have three chiral objects, and now we will discuss chiral interactions within these objects. So
Here, since you are working on with the spin degree of freedom, so how do you describe the wave function in the legend function? In the next slide, you should the PL. So PL, obviously PL is the SP or P or D function of the atomic orbital.
No, atomic orbital, it's molecule. There is no any symmetry coming from the molecule. Molecular orbital doesn't have any symmetry.
Yes.
Look at its shape. There is no any.
I have some picture here, something like that. So molecular orbital, blue is positive, for example, red is negative. It's a constant amplitude of the.
When we consider photoionization from an atom, atomic orbital dictates the L value of the initial. It has definite L value, and this dictates channels where the photoelectron goes, plus minus one.
But actually, it can play a role unless you are only considering scattering of trivial symmetry.
It's not scattering, it's absorption of photon, and then photoelectron goes away in a scattering state, which also doesn't have any symmetry because molecule doesn't have any symmetry.
I see. So the spin is actually related.
Spin of photon.
The spin of the photon is actually related to the angular orbital momentum.
No. Spin of photon and its orbital angular momentum are quite different things. In our case, a photon doesn't have any orbital angular momentum photon. It has only spin. It is zero if it is linearly polarized and plus minus one if it is cyclically polarized to right and left. The photon principle can have orbital angular momentum, and such photons, so-called vortex light, have been created, and but we don't consider this. We consider the usual photon.
Okay.
This question,
Something.
use the legendary function to describe the.
It's not use, it's result.
The key result that the averaged over the molecular orientations partial vortex cross section, partial differential vortex cross section is given by the following formula.
Yeah, there is so-called Young theorem. Young is the same as Young-Mills, which states if you have collision between two particles in L partial wave, then in the output you have up to 2 times L. So photon has one, which is not angular but momentum, but spin, and that's why you have up to 2. So you are right. Yes.
But nevertheless, so what type of atoms, what type of electrons are actually, well, not scattered but emitted by
Vortex.
No. I mean, okay. So for each atom is modeled with what?
No, it's molecule, not atom. It's molecule.
In the molecule.
Each atom in the molecule is modeled by zero range potential.
Okay.
And totally molecular potential is a sum of several zero range potentials. But orbital, you have seen the orbital, right? It doesn't have any symmetry. Because sitting on one center, wave function fills the other center, and many others, all of them.
Right. But okay, so I'll put it in another way. What electrons are emitted? What electrons are emitted? Are there S electrons or
There is no S, there is no P, there is
Something
no
like the
molecular potential. It doesn't have any symmetry. SP and so on comes only if you consider bound state in a spherical symmetric potential. Here, potential is not spherical symmetric.
This is just scattering. So you
Look at this. This is the bound state. Red and blue shows the cut of the either surfaces of the bound state wave function, positive and negative respectively.
Okay, so the molecule structure can bring hybridization. Right.
If you, it's already hybridization if you have mixing of S and P, so-called.
Right.
But it's very, very far from any. This language is not appropriate in this sense. It's molecular orbital. This is called molecular orbital. Junhui mentioned LUMO. This is home.
The home. Okay, I will go ahead.
And first, we have proven that there is the following relation. So if we have some molecular, when we have some we have some coefficients B here, when for the mirror copy of this molecular, we denote these coefficients as B tilde, and where is the relation that B tilde equals to B minus P minus M. It means that if we change from the molecular to its enantiomer, it's the same as change chirality of the photon and chirality of the photoelectron. Okay, this is one of the main relations, and there are also other. For example, if we change polarization of the photon from -1 to +1, so for example, from a left polarized photon to the right polarized photon, when even coefficients B don't change, but odd coefficient L1 change the sign. Okay, and also if we have L equals 2 here, when there is a connection between linear polarized light and circular polarized light. Okay, also let our illustrate chiral asymmetries in parallel for two molecules, N-butan and 2-butanol, which are how to say, we have a lot of in common, but for 2-butanol there is additional atoms here, which makes this molecular chiral. These molecules have the similar size and shape, so the total cross sections have the same form. There is a huge peak here and small peak here, and this is a fractions of vortex photoelectrons. As you can see, for example, momentum 1, where is for example, more than 50% of photoelectrons are chiral vortex photoelectrons with non-zero vorticity. And let's consider, for example, we change the chirality of the photon. Okay, so consider two processes. We have ensemble of the molecular when non-chiral photoelectron and photon with left polarization and the right polarization. When using this formula, we can connect the B coefficients in two situations. For example, in the upper, we have solid red line and dashed red line for the negative polarization. And you can see where is the difference, which is in fact the chiral asymmetry of the problem, because if you change the polarization, if you change polarization of the photon, it means chirality of the photon when these coefficients B1, P0 will be changed.
Can you explain? So experimentally, this must be high energy photons, not visible range, but with energies of several tens of electron volts. Is it easy to produce such photons with specific circle polarization?
Yeah.
How do we do it?
No. Okay. There is experiments with non-vortex photoelectrons, but we produced photons with circular polarization at the energies that we want. So
Control. Huh? And they can control polarization.
Such experiments on photoionization of atoms or molecules beyond the context of vortex electrons, for plane wave electrons, they have been conducted since 60s.
So the new thing is this so-called polarized high energy photons.
They look very high energy, several tens of electron volts.
Still.
Okay, so again, we have the two cases, positive left polarization photon and right polarization photon, and the coefficients B1 will change between these two situations, and it's a chiral asymmetry. The second, for example, we can consider a chiral ensemble of the molecules when chiral photon, and where will be chiral asymmetry in the photoelectrons with positive M and negative M. As you can see, where is a solid lines and dashed lines, and where is the difference between them.
Another question. So experimentally, if we have a gas of this butane or whatever, the spatial orientations of different molecules are random. So probably there should be some ensemble averaging that would make this picture symmetrical.
No, this is exactly the point. After averaging over molecular orientation, some asymmetry remains.
It remains.
It remains only if you have a chiral probe and a chiral object which is probed.
We have to have two chiral objects, like hands. And finally, and for my opinion, the most important, but for example, we have consider linear polarized photon, so it's not a chiral, but two ensembles of left enantiomers of chiral molecule and right enantiomers of chiral molecule. And if we have final state is a vortex state, when by the signal that we measure by these vortex photoelectron detectors, we can distinguish right enantiomers and left enantiomers. So we can distinguish molecules and it mirror copy.
So you don't really need a circularly polarized light for that.
Even without cycle.
Okay.
Because where a lot of papers, a lot of works about how to probe molecular chirality by chiral light, by spin, or chiral structure of light or something like that. But in our picture, when we consider vortex photoelectrons, we now we don't actually need chiral light. We don't need polarized light.
You need a chiral detector.
Yes.
Okay.
So the role of a chiral probe moves from the photons to the detector. And this is one of the key points, but now vortex photoelectrons open a new window for probing molecular chirality. And of course, it will be just a fantasy because, again, we need somehow chiral detector now. Okay, and we propose some idea or sketch of this chiral detector. Recall what these vortex electrons are produced by forked grating, and again it works in the following way. It takes incident wave beam of the incident wave and splits it in a few beams and changed the vorticity of the. So here we have minus L, L, and 0. Okay, and our idea is the following: we have grating, something like that. Here we have gas of randomly oriented molecules. Here is vorticity axis, which we chosen here by n. When on this grating follows flux of vortex photoelectrons with some amplitudes. So this is a vortex photoelectron with different amplitudes AM, and we have to somehow measure this AM. When this grating split our beam into 3 beams without changing angular momentum, changed +1 and changed -1. And here we have a screen where we detect electrons. When we can calculate specific points of this screen, and if you measure the flux at this point, and at this point, for example, we can reconstruct these amplitudes AM. So our vortex detector, chiral detector of vortex electrons, it's a forked grating, which is very similar to this one, and electron detector behind it at some distance. And of course, there is some interferation between different beams, which, how to say, we have some interferation, and of course we cannot measure exact this amplitude. Here is our, how to say, dreams about experiment. The solid line is the exact values of AM for some atom, and dots are AM extracted by this picture. Okay, so we believe that something like that, some of these ideas can be used in real experiments in future. And okay, we have a few minutes, and I would like to say a few words about how mathematically we obtained the main formula. So we have actually 3 coordinate system, three frames. It's a laboratory frame, it's a vortex frame, the vorticity around z-axis, and molecular frame. This frame is frozen into the molecular. When we can calculate, this is how averaging or molecular orientations work. We have dipole matrix element in the molecular frame. This frame is frozen into the molecular, so there is no rotations, and it can be expressed by some coefficients f, which should be calculated somehow. But once we calculated, we know the dipole matrix element in the molecular frame, and when we can rotate it in any frame what we want. For example, we can rotate it into a laboratory frame by Wigner D functions. So we have 2 rotations, and we have 3 Wigner D function to rotate the spherical harmonics. When we squared the amplitude and overaged over molecular orientation, one can calculate the integral over product of 4 Wigner D function by this formula. And when finally we obtain the following formula, and you can see that here is a sum of these coefficients which we calculated somewhere, and there is a sum of L from 0 to 2 over this Legendre function, and this say complex formula can be rewritten in the following form. The coefficients B is given by this sum. Okay, that's how we obtain this formula, and using this exact representation of coefficients B, we can study chiral symmetries of these coefficients B, and that's how we obtain the main results of our work. And so let me once again repeat the key idea that the chiral nature of vortex photoelectrons manifests itself through interactions with other chiral systems, and it enable to develop a new how to say, enantiosensitive spectroscopic methods. Okay, that's all. Thank you for your attention.
Can I ask a question?
Yes, please.
Usually, if you don't look to very high energy photons, just look to the optical activity. Yes, when you have maybe for this molecule, it will be just ultraviolet maybe. And usually for this reason, you use just the Rosenfeld formula. Yes, and for Rosenfeld formula, it just like matrix elements, you need to know just dipole moment and magnetic dipole moment and scalar product of these two moments. And is it very different from your case? Because in your case, your final state may be just a bit different, but is it the same in principle or no?
Okay, thank you. It's a good question, actually. The idea is the following: there is a so-called circle dichroism, is the phenomenon where chiral optically active materials they feels differently for left polarized and right polarized light. It's a circle dichroism, and it's based on, as you said, magnet dipole interactions. Okay,
It's interference between electric dipole and magnetic dipole.
Yeah.
So it's second order in light matter interaction. It's much weaker effect. That is why this rotation of polarization plane in sugar is observed only in liquid phase. We are talking about gas phase, first order in light matter interaction process, photoionization.
when you have magnet dipole moments, there is also 1 over speed of light in front of it. It means that such effects are suppressed by squared speed of light and much weaker when we consider here. Okay, to observe this rotation of polarization vector, we have to use how to say high density of molecules in, for example, liquids or even solid state. But we are talking about gas phase, which much more weaker density.
Okay, it's like because the final state it's really chiral. This how I can understand that.
No,
Yes?
because process different. What you mentioned is so-called secular dichroism. The process is based on interference between electric dipole and magnetic dipole transitions. It's second order in light matter interaction. It's different process, completely different. This process anyway is observable because it's observable in liquid phase. You need high density to see the effect. This process is not observable in gas phase. But there is another process, also chiral sensitive process, so-called photoelectron secular dichroism. It's just photoionization. First order in photon molecule interaction. There's different process. There is no magnetic dipole.
But it's probably also symmetrically different because for this process you need a pseudo vector.
Yes, yes.
And when you average over all
It's
orientations,
completely different. I am saying that process has nothing to do with what Kirill presented.
Okay, thank you.
Thank you for your questions.
Any more questions?
So in a system, so according to the conservation of CPT symmetry, so if you broke the P symmetry, which is parity symmetry, and it will certainly create the chirality symmetry. But now if you preserve P symmetry, it means that your molecule is symmetric, the mirror symmetry. And but you now break the time translation symmetry, no time translation, time reserve symmetry, time reversal symmetry. So will you also observe the chirality in your case? So now T equals to -1 and C It means that you must box the.
Means the sign of M certainly changes. Sign of projection of angular momentum on the vertex axis. So verticity of the
It's like
changes.
Yes.
this formula actually told. Sorry.
But there is that particle photon. If photon is linearly polarized, then that's it. Changing molecular enantiomer at the same, that means violating p symmetry, you and simultaneously changing time direction, you return back.
We have a PT symmetry, right? P symmetry change from molecular to its mirror image, but time symmetry change chirality of photon and photoelectron, because rotation, how to say, rotation this direction in reverse time means like rotation on the opposite direction.
This means you apply a magnetic field to your system, to your molecule. So even it is a mirror symmetry, it has a P symmetry, but the external magnetic field.
No magnetic field, vertex photoelectron. It's a chiral probe. Magnetic field would be another chiral probe.
What is known about lifetime of this chirality in electrons? And chiral electrons, do they live forever, or they fly and somehow it dissipates?
So basically, we're solution of stationary Schrödinger equation. So actually, its lifetime from this point of view is infinity. But of course, in reality,
any scattering will probably affect it. No? Any just elastic scattering would not it lead to the loss of chirality?
After photoionization, we are not like one photoelectron where is a wave pockets, and where is some time evolution. It means that, how to say.
Yes, but it's just interesting. Perhaps there are some fields, random whatever magnetic field of Earth, and it flies. Something happens with chirality or not?
We know what in external homogeneous electric field, where is nothing. External electric field doesn't affect chirality, but magnetic.
Probably it can, because if it flies, there is the wave vector, and you have magnetic field, so there should be some Lorentz force acting on it. So I don't know.
Maybe something like
The answer very much depends on your initial state, which you want to consider, decay, which you want to consider. If it is indeed the exact stationary solution of the stationary Schrödinger equation, it's like plane wave. That means it's everywhere.
Yeah.
Nothing happens with it.
Yes.
But if you start from a wave packet,
yes, of course.
yes, it decays, and eventually you will find plane wave electrons going different directions.
The external electric field might make the orientation of the molecular angular to be different. So this is already proved in the liquid crystal.
But here it results average of orientation. Orientation average.
That's it. Yes. Then even that's not checked. Sure.
Okay. If no more questions, let's thank our speaker again. So for the next time, you will know who will be the speaker next week.
Without Zaur.
We need Zaur. But
sorry, where is the question in the text? Did I catch correctly that photons were considered with circular polarization? What about orbital angular momentum? We considered photons in circular polarized or linear polarized, but they don't have orbital angular momentum. So photons behave like a plane waves in the coordinate. I hope I answered.
okay, thanks very much.
Тут как-то надо специально выбрать.
Остановить.
Вот так, да?
И остановить трансляцию.
Вот это, да?
Да.
Thank you.
До свидания.